Hey everyone, and welcome back. Today we're going to be doing a deep dive into DGA.
Yeah.
It's dissolved gas analysis, right?
Yeah, that's right.
Awesome. So we're going to be looking at an article from the Transformers Technology magazine. It's the October 2024 issue. And this is all about how we could use DGA to monitor the condition of tap changers in power transformers.
Yeah, really important stuff.
Okay. So before we get too far into the weeds here, can you maybe just give us like a quick refresher on what tap changers do? Why are they important in a power transformer?
Sure. So tap changers are used to adjust the voltage in a transformer. They actually can allow us to shift the phase as well, so we can adjust the phase angle. But the main thing is they adjust the voltage.
Okay, so they're kind of like the transmission in a car, right?
Yeah, you can think about it that way. It's allowing us to change gears, so to speak,
Yeah.
and keep that power flowing smoothly.
Makes sense. And the article mentioned that they're actually responsible for a pretty significant number of transformer failures, right?
Yeah, the article said 26% of failures can be attributed to problems with the tap changer.
Wow. So these things are they're super important to keep an eye on, right?
Absolutely. Yeah. And that's one of the reasons why DGA is so valuable, right? It allows us to monitor the condition of these tap changers and identify problems early, hopefully, before we have a catastrophic failure.
Okay, so DGA, dissolved gas analysis, is kind of like an early warning system then for these tap changers.
That's a great way to think about it, yeah. It's like getting a blend test for your transformer. We're analyzing the gases that are dissolved in the oil, and those gases can tell us a lot about the condition of the components inside.
I'm intrigued. So walk me through this. What kind of gases are we talking about? What did they tell us?
So there are a couple of different approaches to DGA. One is called key gas DGA, and this method focuses mainly on hydrogen as an early warning signal.
Hydrogen. Interesting.
Yeah.
Okay.
Yeah. When something starts to go wrong inside the tap changer, hydrogen is often the first gas that will be generated.
Gotcha. So if we see hydrogen levels starting to creep up, that's a sign that something might be amiss and we need to dig a little deeper.
Exactly. But to get the full picture, we often use a technique called multi-gas DGA. And this one looks at a wider range of gases, things like methane, ethane, ethylene, and acetylene. The key here is that different gases are produced at different temperatures.
So it's not just about the presence of a gas, it's also about the amount, maybe the type of gas that's present.
Exactly. Yeah, the combination of gases and their ratios can tell us a lot about the severity of the problem. So, for example, a high concentration of ethylene might indicate a serious thermal fault. Whereas if we see a lot of hydrogen, that might suggest something less severe, like maybe some partial discharge.
So it's like piecing together a puzzle, right? You're looking at these different gases, looking at their ratios, trying to figure out what's going on inside the transformer.
Exactly.
Now, the article mentioned some kind of jargon. I don't know. There were things like T2 or T3 level faults. What do those actually mean? What does that tell us?
Yeah, so those terms basically help us to classify the severity of the problem based on the thermal energy involved.
Okay.
So a T1 fault would represent a lower temperature event, maybe some minor arsing or overheating.
Okay.
A T2 fault would signify a more serious issue with higher temperatures involved.
Yeah.
And then a T3 is the most severe. You could almost think about it like a 5-alarm fire inside your transformer.
Oh, wow. Okay. So the type of gas and its concentration, that can give us clues about the severity of the problem inside the transformer.
Absolutely.
That's pretty amazing. But, the article also mentioned that DGA can tell us something about the condition of the tap changer contacts themselves. How does that work?
Well, as you know, tap changers, they involve a lot of moving parts. And there are these electrical contacts that are making and breaking connections constantly. And over time, those contacts can wear down, which can lead to problems.
Yeah, makes sense.
And what DGA allows us to do is to actually detect that wear and tear by analyzing the gases that are generated during the arsing process.
So the arsing itself, like that action, is producing gases that can tell us something about the health of the contacts.
Yeah, you got it.
Wow.
The article even mentioned this term, a good arsing signature. Essentially, if we have a healthy, sealed tap changer, we expect to see specific ratios of things like hydrogen, acetylene, ethylene, and methane.
Okay, so that's like the ideal, right? Those are the ratios we want to see. But what happens when things are not ideal? What happens when that signature isn't so good? What kind of problems can DGA help us catch early on?
So one example would be excessive contact wear. As those contacts wear down, the arsing gets more intense. And as the arsing gets more intense, the gas ratios start to shift away from that ideal that we talked about.
So if we see those ratios changing, that's kind of a red flag that those contacts might be wearing out.
Exactly.
Oh, interesting.
And there's actually a formula that we can use to assess this contact wear. It's called Stennis-Stam's ratio. It's a little bit technical, but basically it looks at the ratios of methane, ethane, and ethylene compared to acetylene.
Stennis-Stam's ratio. Okay. I'm going to have to write that one down. Can you maybe break that down for me a little bit? What does that ratio tell us?
Sure. Think of it this way. A higher Stennis-Stam's ratio means your tap changer is getting hotter, and it's moving closer towards failure.
Oh, wow. Okay.
If that ratio is below 0.5, generally speaking, that suggests that there's no overheating going on. But if it starts to climb above 0.5, especially if it keeps increasing, that's a sign of potential overheating and contact wear.
Oh.
And if it hits 5.0 or higher, well, that's a clear indication that we've got active overheating going on, and it's time for an immediate inspection.
Okay, so DGA doesn't just tell us that there's a problem. It can actually tell us, like, how serious that problem is.
Right. And that allows us to prioritize our maintenance activities, right? So if we see something that's really critical, we know we need to address that right away.
This is incredible. Now, the article mentioned that the design of the tap changer itself can actually influence the DGA results. There was something about sealed versus free-breathing designs.
Right. That's a really important distinction. A sealed tap changer, as the name implies, is completely enclosed.
Okay.
The oil and gases are contained within that sealed unit, but a free-breathing tap changer has vents that allow some of the gases, particularly hydrogen, to escape into the atmosphere.
Oh, interesting.
And this can have a big impact on the DGA readings. For example, you might see lower hydrogen levels in a free-breathing tap changer simply because some of that gas is escaping.
Wouldn't that make it harder to get an accurate reading, though? I mean, if gases are escaping, wouldn't that skew the results?
Well, it's true that some gases might be escaping, but we can still get valuable information from the DGA. We just have to take the design into account when we're interpreting those results.
Okay.
So, for example, in a sealed tap changer, the nitrogen to oxygen ratio should be pretty stable. But if we see a sudden spike in oxygen, that could indicate that there's a leak and air is getting into the system.
Oh, gotcha. Okay, so even with free-breathing tap changers, DGA is still a useful tool. We just need to kind of adjust our thinking based on the design.
Exactly.
Gotcha. Now, one more term that I remember seeing in the article was vacuum OLTCs. What are those all about?
So vacuum OLTCs, these are a newer type of tap changer technology. And instead of the arsing happening in the oil, it actually occurs inside a sealed vacuum bottle.
Oh.
So the contacts are making and breaking connections in a vacuum, and that eliminates the risk of fire or explosion.
That sounds much safer. But if the arsing's not happening in the oil, is DGA even useful in this case?
It's a good question. It might seem counterintuitive, but DGA is still incredibly valuable with vacuum OLTCs, because if we see any combustible gases in the oil, it means that that vacuum bottle has failed, and that requires immediate attention.
So it's like a canary in the coal mine, right?
Yeah.
Any presence of those gases is a sign that there's a serious problem.
Exactly. A failed vacuum bottle can lead to a major transformer failure if it's not addressed quickly.
This is fascinating stuff. I feel like we've covered a lot of ground here, from the basics of DGA to these different tap changer designs. But before we wrap up part one here, is there anything else that our listeners should really keep in mind about this technology?
Yeah, I think the most important takeaway is that DGA is an incredibly powerful tool. It's a window into the internal workings of these machines. It helps us to detect problems early and take corrective action before they escalate.
You don't want to wait till it's too late, right?
Absolutely not. You want to catch these problems when they're small and easy to fix.
So it sounds like DGA is really essential for anyone who's responsible for keeping the lights on.
Absolutely. It should be part of every utility's asset management strategy.
We'll definitely have to dig deeper into the practical applications of this technology in part two. But for now, thanks for sticking with us. We'll be right back.
Sounds good. It really is. It's like having a superpower when you're trying to keep these critical pieces of equipment running smoothly. It helps us move away from just reacting to problems, waiting for something to break. And instead, we can be more proactive and hopefully prevent those big failures from happening in the first place.
Okay, so let's talk about putting this superpower into action. If you were in charge of a fleet of transformers, how would you actually implement DGA monitoring? What are the steps involved?
Well, the first thing is to make sure that you're monitoring all of your transformers that have on-load tap changers, right?
Right.
And you can do this through periodic oil sampling, sending those samples off to a lab for analysis. But the real game changer here is online DGA monitoring.
Sure.
These systems, they give you continuous real-time data, which allows you to detect and respond to problems much faster.
So online monitoring, that's like having a constant stream of information about the health of your tap changers. You don't have to wait for those lab results. You can see what's happening as it unfolds.
Exactly. And that speed can be really crucial when you're dealing with a potential failure. But it's not just about collecting the data, right? It's about knowing how to interpret that data.
Yeah.
I would make sure that my team is well trained, that they understand those gas ratios and signatures that we talked about earlier. They need to be able to look at the data and say, okay, this hydrogen spike, that's probably nothing to worry about. It's a minor issue.
Yeah.
But this rising stenostams ratio, well, that's something we need to address right away.
Right, right. So it's not just about having the fancy technology. It's also about having the expertise to use it effectively.
Exactly. And there's another really crucial aspect to DGA that we haven't really talked about yet, and that's trending. By tracking these gas levels and ratios over time, we can identify subtle shifts that might indicate an emerging problem, even if the readings are still within acceptable limits. You know, it's like, think about it like your blood pressure. Let's say your blood pressure has been slowly creeping up over time. It might not be a cause for alarm right now, but it's definitely a sign that maybe you need to make some lifestyle changes to prevent bigger problems down the road.
Yeah, it's a great analogy. So it's all about being proactive, right? Noticing those trends and addressing potential issues before they become major headaches.
Absolutely. DGA is a powerful tool for asset management, helping us get the most out of our equipment.
So we've talked about all the great things that DGA can do, but are there any limitations? Are there situations where it might not be as effective?
That's a good question. While DGA is a really powerful diagnostic tool, it's not a silver bullet. There are certainly situations where it might not give us all the answers. For example, DGA might not be as effective in diagnosing certain mechanical problems within the tap changer, things like worn gears or a faulty drive mechanism. These kinds of problems might not produce a clear gas signature that we can pick up with DGA. So in those cases, we would need to rely on other diagnostic techniques like vibration analysis or visual inspections.
So it's important to remember that DGA is just one piece of the puzzle, right?
Exactly. We need to use it in conjunction with other tools and techniques to get a complete picture of the tap changer's health. It's all about using the right tool for the right job. But even with those limitations, you know, DGA remains one of the most valuable tools we have for monitoring tap changers and preventing transformer failures.
And it seems like it's a field that's constantly evolving, right? There's always new research and development going on. Are there any new developments or advancements in DGA technology that you're particularly excited about?
Oh, absolutely. One area that's really pushing the boundaries is the development of advanced algorithms and machine learning techniques for DGA interpretation.
Oh, interesting.
Yeah, these tools can analyze vast amounts of data and identify subtle patterns that might not be apparent to the human eye.
Wow.
They can also help us to predict future failures with greater accuracy, which is really exciting.
It's like having a superpowered DGA analyst working 24/7, sifting through all that data and alerting us to potential problems before they even occur.
Exactly. It's a really exciting time to be working in this field. We're seeing a convergence of technology and expertise that's going to revolutionize the way we monitor and maintain our critical electrical infrastructure.
This has been an incredibly insightful conversation, really a deep dive into the world of DGA and tap changers. I think our listener is well on their way to becoming a DGA expert themselves.
I hope so. It's a fascinating and really vital area of power system engineering.
Before we move on to the final part of our deep dive, maybe we could just take a minute to recap some of the key takeaways here. So we've learned that DGA is a really powerful technique for monitoring tap changers, preventing those transformer failures that can be so costly and disruptive. It involves analyzing dissolved gases in the transformer oil to identify problems early on. And we talked about how different gases and their ratios can tell us a lot about the severity of a problem. Don't forget about Stenostams ratio. A higher ratio means more heat and more trouble for your tap changer. We also discussed the different types of tap changer designs, like sealed and free breathing, and how those designs can influence those DGA results. And of course, we talked about the importance of online monitoring, trend and data, and using DGA in conjunction with other diagnostic tools. It's safe to say that DGA is no longer just a technical curiosity, it's a vital part of ensuring the reliability and resilience of our power grid.
I completely agree.
Now, in part 3, we'll shift gears a little bit and explore some of the broader implications of DGA and its role in the future of power systems. So stay tuned. All right, so we've talked a lot about how DGA can help us keep those tap changers running smoothly. But you mentioned earlier that our electrical grid is, well, it's facing some pretty big challenges right now.
Mm.
What are some of those challenges, and how does DGA kind of fit into that bigger picture?
Well, I think one of the biggest challenges we're facing is just the age of our grid infrastructure, right? A lot of our transformers, a lot of these tap changers, they're getting pretty old. They're nearing the end of their expected lifespan. And that puts a lot of strain on the system.
Yeah, that makes sense.
And at the same time, we're seeing this incredible increase in demand for electricity.
Yeah.
You know, our society is becoming more and more electrified. Everything from electric vehicles to all those data centers that are popping up everywhere.
Right, right. So we've got this, like, perfect storm brewing, right? We've got an aging grid. We've got growing demand. Sounds like that could lead to some serious problems.
It definitely could. And that's where DGA becomes even more crucial. By proactively monitoring the health of our transformers and tap changers, we can extend their lifespan, avoid those costly replacements, and prevent those disruptive outages that nobody wants.
So DGA is not just about fixing problems when they happen. It's actually about optimizing the performance of the equipment that we already have.
Exactly. Squeezing every last bit of life out of those assets.
Now, you also mentioned that DGA is playing a key role in integrating renewable energy sources into the grid. I'm curious, how does that work? How does DGA relate to renewable energy?
Well, as we bring more solar and wind power online, the grid becomes a lot more complex and a lot more dynamic. You know, the output from those renewable sources, it's not always constant. It can fluctuate depending on the weather conditions, and those fluctuations can actually put additional stress on our transformers and tap changers.
I see.
And DGA allows us to monitor that stress, make sure those components can handle that variability.
So DGA is, in a way, helping us build a more resilient, a more sustainable grid.
It is. And there's another aspect of DGA that I think is becoming increasingly important, and that's data analytics.
Okay.
You know, as we collect more and more DGA data from transformers across the entire grid, we can start to see these larger patterns and trends that might not be obvious when you're just looking at an individual asset.
So it's like big data for the power grid.
Exactly. We can use that data to identify emergent issues, predict potential failures before they happen, and even optimize our maintenance schedules across the entire grid.
So we're talking about some serious efficiency gains, some serious cost savings here.
Absolutely. And it's just one example of how DGA is evolving beyond a simple diagnostic tool and into a powerful platform for grid management and optimization.
Wow. This whole conversation has been a real eye-opener. It's incredible to see how this technology, something that focuses on these tiny little dissolved gases, is actually playing such a huge role in shaping the future of our power grid. Any final thoughts for our listener before we sign off here? Anything they should keep in mind as they, continue to explore this topic?
Yeah, I would just encourage everyone to stay curious, keep learning. DGA is a fascinating field, always something new to discover, and it's only going to become more important in the years to come as we face these growing challenges to our electrical grid. There are a ton of great resources out there, industry publications, technical forums. Don't be afraid to reach out to experts in the field and ask questions. I think you'll find that a lot of us are really passionate about this technology and happy to share what we know.
That's great advice. A huge thank you to you for joining us today and sharing your expertise. I know I've learned a ton, and I hope our listener has too.
It's been my pleasure.
To everyone listening, thank you so much for joining us on this deep dive. We hope you found it insightful and maybe even a little bit inspiring. The next time you flip on a light switch, maybe take a moment to appreciate those tap changers working behind the scenes and this incredible technology that helps us keep them running smoothly. Until next time, stay curious, keep exploring, and we'll catch you on the next deep dive.